I choose you.
Fight!
Yes, that is right. I did choose a USC internship upon completing my UCLA internship. Meaning, I kind of had to throw away all my UCLA stuff. No, not really. Not to say that I was mad that I got this internship. I was actually happy because how funny and how often does somebody get to say, yeah man, I got an internship at UCLA. And you know what I did after? I went to USC. It's more common than you think, and it usually is, where UCLA students go to undergrad there and then they realize that going to a prestigious school isn't everything and they need those connections. So where do you go? The one place where you could buy connections. So in this episode, I'm going to continue on with the series that I initially stated in the last video that I was going to start, which was me going over my experiences within the college system and exactly what internships I did to make me the engineer that I am today. So in this episode, I'm going to show you exactly what I did to earn a USC internship in their rocket propulsion laboratory. So real quick, if you haven't seen the other video that I did about my UCLA internship at a mechatronics and controls laboratory, make sure to go watch that because there is a little bit of information that I went over in that video that I'm not really going to bother to go over in this video. This was another community college program. So this is about 2015. I have just finished my internship at UCLA. I'm feeling good. It's about fall of 2015 and I'm getting ready to apply to different universities and primarily UCs to get into the year of 2016. Keep in mind, I've been very strategic with what I would do in my spare time and what projects I would be involved in. This is just something that set me up for me to get into my dream school at the time, which was UCLA. I had put all my resources into getting into this one school and I finally had an internship there, so I thought, great, I'm gonna have the perfect personal statement to tell the admission officers that I deserve a spot at UCLA. We'll talk about that later. There was a HENOC conference in Pasadena in about October of that same year that I finished the internship. So give or take 2 months after I did that internship, I went for a poster competition at Great Minds in STEM HENOC conference. And I actually didn't place, but I really got a lot of experience because I was able to talk to other engineering students, professors, professionals about my research, and that was great exposure for me. And because of that, I kind of got exposed to many more opportunities as far as what industry internships there were. It was there where I met with one of my advisors in Mesa, and we got to talk a lot more about different programs, and they mentioned this program called the Base 11 program. Base 11 is a nonprofit that gives undergraduate students, primarily community college students, hands-on experience in industry and also engineering and STEM fields. And I owe a huge thank you to the people at Base 11 because they were really the people that believed in me through the whole process. They looked at me as an individual and not as some person that I used to be, and really saw the passion that I had for engineering. And keep in mind, I was so excited the fact that I had gotten a internship at a laboratory that I decided to kick it up a notch. If you didn't see the last video, I said that I applied to 3 different internships, but I thought about the quote that Wayne Gretzky would always say, or if you've seen The Office, Michael Scott, it says that you miss 100% of the shots that you don't take. And I took that to heart. I really did. And I decided, well, why not apply to 20 different internships? And I did. I applied to Harvard. I applied to Yale, MIT, University of Chicago, Washington, Berkeley again, UCLA again, USC, San Diego, you name it. I was on a roll and I was like a madman trying to find my next opportunity for where I was going to grow. So what was different from the Base 11 internship process was that at Base 11, I actually talked to the CEO of the company. And for me, this was a huge privilege and honor to be able to talk to the CEO personally. We talked for I think about an hour, and I really think that that helped me showcase my personality more, because shortly after I was invited to the program. They did have an internship at USC, they had another one at Caltech, they had one at the Smithsonian in Washington DC, and I applied to the USC one because I said, well, why not? And I would be working in the mechanical and aerospace department, primarily in aerospace. So before the program started, I had no idea what was going to go on. I just knew that it was geared towards aerospace engineering. So I did do my research, and I did do as much as I could as a community college student to prepare myself for this internship. Little did I know is that I was getting myself into quite a summer. And I say that in the most positive way possible because this internship pushed me to new heights. So I'm going to give you a little background real quick about the program perks. I was also getting paid for this internship the same way I was getting paid for the UCLA one. This is the kicker. I had my own apartment and I was sharing it with 3 other people that were a part of the program. 2 out of the other 3 were in my team and the other one was a computer science student. In addition to that, it was USC. I live in South Central, which is probably 10 minutes south of USC. So it's pretty crazy because I grew up always passing through USC. I passed there all the time as a kid. I would look at all the students and I would just think like, oh my God, this is so cool. Like, I want to be somebody like this one day. And sooner or later, it ended up becoming a reality. It's so funny. And I said it in the last video, everything happens for a reason. I really wanted to live on my own in an apartment. I just couldn't afford it. And law of attraction for you, I ended up getting an apartment and it was the most incredible thing ever because it was in front of USC. Being able to eat at the Commons, which in my opinion weren't as good as the UCLA ones, but that's going to be our secret. But also being able to work under another department chair. That's right, I was able to work under Dr. Geoffrey Spedding, not to get mistaken with Joffrey, the evil person from Game of Thrones. He was a very nice person, and once again, he was the leading researcher in aerospace engineering and something that I'll talk about later called PIV. But in addition to working with Dr. Geoffrey Spedding, I was also able to work with Dr. Wilson Chan. And even though he was an associate professor, this guy knew his stuff and he taught us as much as he could. And it was the first time I was actually able to sit with the professor as much as I wanted and just learn. And if you don't know already from the last video, I was very eager to learn as much as I could because I knew how crucial this was in securing me a job in the future. So the first week was just like the other internship at UCLA, was just learning the material. And I would say we were at a huge disadvantage, primarily because we were community college students. I had just found out that I got accepted to UC Irvine and I had committed there, but I still didn't take any of the upper division classes. So we actually had to learn everything within that summer. Dr. Wilson Chan came into our office and dropped down like 4 huge books, these huge textbooks explaining low Reynolds number, explaining aerodynamic characteristics, a fluid mechanics book, and about this much of previous papers on the subject. We had to determine whether or not a program that was made by an MIT professor called X-Flyer 5 was a viable resource for the lab and for other technicians in the aerospace field to use to accurately characterize different airfoil characteristics that you would typically have to test in a wind tunnel. So the airfoil that the professor chose was a NACA 0010 airfoil. It was a symmetrical airfoil, meaning that the top and the bottom were exactly the same. The aerodynamic characteristics would be more consistent from the top and the bottom, whereas if you had an asymmetrical one where it would either create more drag or lift within the airfoil. Great example of this is a spoiler. If you notice, most spoilers, they're not very symmetrical, and that's for a reason. They usually have some type of tail in the end, and that is to create more drag, because drag is needed for a lot of high horsepower applications, because you want to have the rear end planted down as you're delivering all the power through the drive shaft into the differential into the rear axle. So in this case, we wanted to test the NACA 0010 being a symmetrical airfoil with the results from actual wind tunnel testing to the program X-Flyer 5. And the program X-Flyer 5 is pretty cool. It has a directory of different airfoils. It varies from asymmetrical to symmetrical. But regardless, you're able to get your coefficient of drag to coefficient of lift charts, which is exactly what most engineers use to determine whether an airfoil could be used for their application. So going into this, the professor did ask us if we wanted to use Excel or MATLAB, because as you can tell, we were going to be going through a vast majority of different values from both the wind tunnel testing and the program. And obviously I've known Excel since I could remember, but like I said, I wanted to challenge myself, and I knew MATLAB was something that I've been wanting to learn, and I know that it's used tremendously in the engineering industry, automotive, aerospace, you name it. It's a great tool for data analysis and data manipulation. I decided to do the same thing that I did at UCLA with SolidWorks and do it with MATLAB. So if you can guess, in a week I read an entire Introduction to MATLAB book, which is right here. It's called MATLAB for Engineers. So I did all the exercises, created my own programs, the programs that were in the book, until I felt comfortable with it. So over the past century, applied aerodynamics has been used to characterize whether or not MAVs or micro air vehicles can be used in low Reynolds numbers, and primarily Reynolds numbers lower than 200,000. Now, Reynolds number is just a ratio between inertial forces and viscous forces. A general equation for this would be Reynolds number is equal to rho times ux over mu, where x is the characteristic length of the airfoil cord, mu is the dynamic velocity of the fluid it is traveling in, rho being the density of the fluid, and u being the velocity that the vehicle is traveling in. From these Reynolds numbers, you're able to determine the lift and drag of an object. You put a to scale model into a wind tunnel and measure its different aerodynamic characteristics depending on the angle of attack. Now, angle of attack being angle in which the vehicle is to relation to a horizontal surface. If you've ever seen a plane take off from an airport, you notice that it goes through a runway and immediately it starts pointing its nose up, therefore creating an angle of attack. And this angle of attack ends up creating a high pressure zone under the vehicle and a low pressure zone over the vehicle, creating the phenomenon lift. And vice versa with cars, like I mentioned earlier with spoilers, if you have a higher pressure gradient on top versus than on the bottom, then you're going to create drag, and that's what you want for your rear end to stay planted to the car. Now, it is very important to keep angle of attack into consideration when creating vehicles, because each vehicle has what's called a stall angle. If the vehicle reaches the stall angle, then the vehicle then loses all aerodynamic characteristics and is no longer able to be controlled. So over the past century, we have countless research, countless papers, countless theories on what happens with Reynolds numbers that are high enough for larger vehicles. When the Wright brothers began testing their vehicles, it was for a fairly large vehicle. Now in modern times, we're moving more towards drones, smaller vehicles, for obvious reasons, for its stealth, for its maneuverability, and for its compact sizing. Unfortunately, the research has not caught up to it, and Reynolds numbers lower than 200,000, well, there's no real way of actually testing it theoretically without putting it inside a wind tunnel. So our main objective was to see if XLR5, the program that I mentioned earlier, was able to accurately predict these aerodynamic characteristics for Reynolds numbers lower than 200,000. So our approach for this was to have our NACA 0010 airfoil within the wind tunnel and to change its angle of attack from -4 degrees upwards to 13 degrees, and also change the Reynolds number ranging from 40,000 upwards to 180,000. Now, this was a good range. We could have gone lower, but we wanted to stay in the safe side to make sure that we didn't get any turbulent flow. Turbulent flow is the unsteady flow of a fluid. So if you've ever seen a stream and it has very straight lines going through the stream, that means the flow is laminar. Now, if you ever see the edges of the stream, you see that it is getting stuck to the walls. That is because the viscous forces is greater than the inertial forces. The inertial forces is the steady stream. So as you get further away from the walls, then your boundary layer is reduced and it becomes less turbulent. You might have been on an airplane once and you've heard the overhead saying, oh, we're going to be reaching some turbulence, make sure to buckle up. So turbulent flow is fluid motion characterized by chaotic changes in pressure and flow velocity. Turbulent is all messed up and is going all over the place and it's unpredictable. There's a lot of spontaneity there, whereas laminar flow follows a parallel line and is continuous and has characteristics that can easily be recorded. We wanted to make sure that we had within the wind tunnel. So as we began our testing, we had to make a program with using LabVIEW to record the values using the pitot tube. Within the wind tunnel, we had two pitot tubes. We had an upstream pitot tube and we had a downstream pitot tube. Now, what that allowed us to do is to get an accurate, consistent reading of the velocity of the wind tunnel upstream before it hit any interruptions like the airfoil, and we also had one behind it. Now, the upstream pitot tube was stationary. It was just to give us a basic value and made sure that we had the correct wind velocity that we wanted to test for the airfoil. Now, the downstream pitot tube was the one that was actually sweeping through each layer behind the airfoil after it has disrupted the flow of air. Now, the disturbance that we were finding behind the airfoil is something called the wake deficit, and that is characterized by the momentum deficit integral, and that is just the sum of different velocities over time. As you can see, as the pitot tube makes its way towards where the actual airfoil is, we see a huge decrease in velocity. That is the decrease in velocity that is caused by the airfoil. So after finding that value, we did notice that towards the bottom of the charts, we did have a little bit of a boundary layer that was occurring. And like I mentioned earlier, a boundary layer is just the wind physically actually sticking to the walls because it does not have enough inertia to push it through. Since air is a compressible fluid, we were getting some higher pressure gradients in the bottom of the airfoil. So when gathering all this information from LabVIEW, I had to change these Excel files and import them into MATLAB. And within MATLAB, I was able to manipulate the values to get the correct order of things that I wanted. Things that I wanted to see were how boundary layer were affecting the wake deficit of the airfoil. And also I wanted to see how the chart was starting to look with the different angle of attacks and the different Reynolds numbers. So from the beginning of the internship, we already ran xFlyer 5 and we knew exactly what the program was spitting out. So we had an idea of what the chart was supposed to look like. So as I started putting the different coefficient of drag over coefficient of lift values versus angle of attack, I started to see the trend occur. However, the trend was either off because of our testing, or the xFlyer 5 program was off because of the way it was programmed. So after getting 1,000 lines of code done and manually adjusting all the boundary layer errors that we found, we finally got a graph that looks something like this. So as you can see, we have the test for Reynolds numbers of 180,000, and you have the xFlyer 5 program, and then you have the wind tunnel testing in red. On the other graph, you have a coefficient of drag over angle of attack, and as you can see, we have a variety of different graphs here. We move over to 100,000 Reynolds number, and we see the characteristics also match. And when we move to 40,000 Reynolds numbers, we also see the characteristics match, but we have these huge error bars. These error bars are here because of the amount of turbulence that we found within the system. So since we were dealing with laminar flow, we were noticing a phenomenon called laminar separation bubbles. So as fluid is moving through the airfoil, it wants to stick. It wants to stay onto the airfoil. However, as you change the angle of attack, it gets harder and harder for the fluid to actually stick to the object. So what you end up getting is a bit of turbulence behind the airfoil as you increase the angle of attack, better known as vortices, and those vortices end up creating a bubble. Since the flow is still laminar, there's some occasions where the flow actually reattaches to the airfoil and disrupts the force balance that we had inside the wind tunnel. After realizing that this phenomenon was occurring, a small correction factor was implemented into the code that I had written, and just like that, we had correct values. The correction factor that I used was 0.75. So by implementing this correction factor to all the data, this is what happened. We ended up getting accurate values. If you look at these charts from before and after the correction factor, the results are incredible. As you can see, as we match up the coefficient of lift versus angle of attack, the values on the graph are very similar. So we did involve a couple errors that might be coming from the tolerance from the force balance, from the pitot tube, and also the compressibility of the air. So why is this important? It's important because engineers and the aerospace industry can now use this program when developing micro air vehicles. This is very important, especially for companies like Amazon that are trying to implement one-day shipping by drones. You have to have these drones able to withstand the realistic aerodynamic characteristics that is going to be involved in creating a smaller, more compact vehicle. This can also carry over to smaller surveillance drones, to military application, you name it. Now you eliminate the need to have a wind tunnel because now you could use this program that was developed for that mine specifically, which is to expedite the process between predicting these aerodynamic characteristics with whichever airfoil that you need. Granted, we did only use this program for the NACA 0010 airfoil, which is a symmetrical airfoil. Therefore, there's a lot more testing that can be done for non-symmetrical airfoils that could also help in the industry. The process was incredible. I was able to work in a lab and actually control a wind tunnel. I was able to understand physically and theoretically how fluid mechanics works. There's one thing to actually learn in a book what a wake deficit is or a laminar separation bubble is, but until you physically see it within data, you really understand what the book is talking about. This was worthwhile because, like I said, I was able to work with LabVIEW. I was able to improve my skills in MATLAB and data manipulation. It made me that much more passionate about the aerospace industry, especially when you're in a lab that's doing PIV. PIV stands for particle image velocimetry. You might see this in a lot of automotive commercials where they put some smoke around a car and you could notice the streamline of a car and see how smooth it is. You know, at this point, you're able to kind of get a better picture of what they mean by coefficient of drag. In all reality, it's just another way of flow visualization. However, in this, you're able to see it in real time. And it's just another way to document exactly the same thing that we're doing, which is getting aerodynamic characteristics. And that's what the graduate students were using. They were using PIV for all their testing, all their thesis, all their dissertation information was coming from PIV testing. And being able to see that firsthand and actually set up a couple jigs for them was incredible, because not a lot of people have that opportunity, because this is a multi-million-dollar system that they have, and they let a community college student help them in their testing. It makes me feel so grateful to have this opportunity that Base 11 gave me and aid in the aerospace industry. The experience wasn't as influential as UCLA as far as building the community that I said that a lot of community college students are robbed of. However, it did teach me a sense of independence, and not only in my personal life, but in my academic life and professional life as well. I had to really just sack up and say either I'm gonna learn this or I'm not gonna learn this. And there's been many times where I just beat my head and I can't learn something, but I have to persevere. And I really aid you guys to also persevere, because this internship was not easy. It was probably the hardest thing that I've ever done, given the fact that I was a community college student that had to learn all of fluid dynamics in a summer. In addition to that, MATLAB. Now, upon completing the internship, I was more empowered than I've ever been in my life. Not just because this was my second internship, but because it really proved to me that the limits are endless. The limits are endless for me. The limits are endless for you. And I really hope you take something out of this. It's not me bragging. It's me sharing my experience and letting you know that your time is gonna come. I had to wait so long for my time to come, but when the opportunity presented itself, I made sure it wasn't gonna slip away. And that's the most important thing that you have to get from this. Whatever opportunity is given to you, make sure you grab it and chokehold it and never let go of it, because it could be gone like this. I really hope you like this video. Like I said, I want to continue doing videos like this on my internships, my projects, my different classes, and give you my 2 cents on how the process went for me, how the experience went for me, what I did, how I did it, the obstacles that I faced, the obstacles that I overcame, the things that I learned, and the memories that I created. And I hope this encourages you, and I hope it really helps you get a better understanding of what it's like to intern at a rocket propulsion laboratory at USC. Before I go, make sure you give this video a like if you really enjoyed the content. Make sure to subscribe if you enjoy the content so much that you want to keep seeing my content. And also give a comment down below about your experiences within the engineering industry and what internships you've gone through. I really want to create a community where people feel empowered to pursue engineering, because like I said, you don't have to be the smartest, you just have to be the hardest working individual in the room. Never stop grinding, never stop pushing, never stop persevering, never give up. Like always, stay boosted. Fight!